Hello, and welcome to a lecture on phasors. My name is Steve Ellingson. A phasor is a way to describe a sinusoidal waveform as a single complex valued number. Engineers like phasors because they make practical work easier. So let's begin with Eulers' formula. Here it is. E, the constant E, raised to the power j times theta, where theta is just some variable, is equal to cosine of that variable, cosine theta, plus j times sine of that variable. And of course j here is by definition the square root of -1. That's Euler's formula. It's really the basis for everything we're going to do in this lecture. Here's something that comes out of that relationship. If a is a real valued constant, I can multiply this thing that I had here by a and take the real part. When I do that, I get the real part of now the expanded quantity, a cosine theta plus j a times sine theta, which is simply a cosine theta. The simple operation is the enabling mathematics behind phasors. So to see why, let's talk about properties of sinusoids. Any sinusoid at all, can be written in the form that I've shown here. A, some real valued constant, times cosine, where the argument is omega t, omega is frequency, that's angular frequency, radians per second, plus some constant here, which we generally take to be the phase. In other words, any sinusoid can be described as a frequency, here we've used omega, and a magnitude, here we've used a, and phase, here we've used psi. So now let's apply Euler's formula to this idea. I'm going to do the following operation. I'm going to take the real part of a times this quantity, where you'll see that this is the argument of the cosine function. And when I apply Euler's formula, I get the same thing, but now I've replaced that complex exponential with the result that I get from Euler's formula. And when I take the real part, I get a cosine omega t plus psi. In other words, this thing is the same as this thing. Now let's go one step further. What I'll do on the left is I will take this complex exponential and break it up into two factors. E to the j psi, which you'll see has to do entirely with the phase of the sinusoid, and e to the j omega t, which has to do entirely with the frequency of the sinusoid. So here we have phase, and here we have frequency, and then of course magnitude here. If we can agree to stick to a single frequency omega, in other words, if everybody agrees on the value of omega in some particular analysis, then this complex number, the one I've indicated here, a times e to the j psi, completely describes the sinusoidal waveform, because we'll have agreement already on what omega is. We've already agreed to that. The remaining two parameters are magnitude and phase, and here they are, magnitude and phase right here. This is what it means to be a phasor. It is simply a complex valued number, this one right here, which completely describes a sinusoidal waveform. It is a single number that describes an entire waveform. And to do this, the deal is we have to agree on omega. So let me show you some examples of phasors. First of all, because every phasor is simply a complex valued number, I can show it on the complex plane. So what I have here is the real axis, the imaginary axis, and so any possible phasor, and hence any possible sinusoid, can be represented as a point in this complex plane. So for example, this point right here is a sinusoid, specifically this one shown here. It has a phase of 0, that's a sinusoid with a phase of 0. It has a magnitude a sub m, that distance is a sub m, and the frequency is assumed and suppressed. Here's another phasor, also representing a time domain sinusoid. Here the magnitude is the same, a sub m, but it has a phase psi. That sinusoid is the one shown here. It's identical to this sinusoid. The only thing that's different is the phase shift, psi. So this change in position in the complex plane, that change in the phasor, represents a different sinusoid, namely one with that phase shift. A third example is this phasor here, AM minus JBM. And AM and BM we'll say are real valued quantities, both greater than 0. In this case, the magnitude of the sinusoid that this represents is square root AM squared plus BM squared. Like so. That's the magnitude of this complex value here. And the phase is inverse tangent BM over AM, as you'd expect simply from the properties of complex valued numbers. A third possibility is this phasor here. It's completely imaginary valued, and it corresponds to this sinusoid. The magnitude of this sinusoid here is A sub m, and the phase of this sinusoid is simply pi over 2, because the phase angle from the real axis to this axis here is pi over 2 radians. Let's look at this whole process of conversion between sinusoidal waveforms and phasors a different way. So here I have a sinusoidal waveform, in fact every possible sinusoidal waveform, something which has a magnitude, something which has a frequency, something which has a phase. And here I've got the description of the corresponding phasor, namely that magnitude multiplied by e to the j psi, where the frequency omega has been assumed and suppressed. To go from the phasor, the complex value, back to the sinusoidal representation, we reattach the frequency phase factor, this part. Right, so we take the phasor, C, multiply by e to the j omega t, the part that we assumed and suppressed, and take the real part, which lands us here. And you can verify that math for yourself. It's essentially the same thing we've been doing in previous slides. To go in the other direction, from a sinusoidal waveform to a phasor, what we do is we figure out how to write the sinusoidal waveform in the form real part, magnitude of c, e to the j psi, e to the j omega t. And then this part is the phasor, the magnitude of c, e to the j psi. Here's an important idea. Equal phasors correspond to identical waveforms. In other words, phasors correspond to waveforms and vice versa. If two sinusoids are equal, then of course the corresponding phasors are equal. I think that's self-evident. If two phasors are equal, in other words, equal to the same complex number, and the suppressed frequencies are identical, in other words, we're continuing to agree on the frequency that we've suppressed in this operation, then the associated sinusoids are identical. Let me say that again. If two phasors are equal, then their associated sinusoids are equal. That's a pretty simple proof, and you can find that in the book. But this is key because it enables phasors to stand in as waveforms. And I don't know about you, but given the choice between dealing with complex numbers and dealing with waveforms, I would rather deal with the numbers. Here's another piece of the answer to the question why phasors are so useful. And that's because we can do some interesting things as long as we stick to linear operations. So first, what do I mean by linear operation? A linear operator, and I'll use the symbol T to refer to these generically, the whole class of things we might call linear operators, are those that satisfy superposition. So what do I mean by superposition? Well, T, the operator T, applied to two operands should equal T applied to the first operand plus T applied to the second operand. That's the property of superposition. And that's, in turn, something that makes the operator linear. Linear operators, in other words, those satisfying superposition, include addition, multiplication by a constant, but not multiplication in general, just multiplying things by a constant, differentiation, integration. These are all linear operators. Now, why this is so useful in the phasor domain? Well, an amazing fact is that if you apply any linear operator to this thing that we have used to define phasors, then you can exchange the linear operator and the process of taking the real part. So what this equation says is that it doesn't matter whether you apply the linear operator to the real part or whether you apply the operator first and take the real part of the result, you get the same answer. Again, this is a simple proof. You can find it in the book. So here's a useful example, and one which is directly relevant to us when we're doing electromagnetics in particular. Also when we're doing signal processing, applies in many disciplines within electrical engineering. When we differentiate with respect to time, in other words, we take this operator as the linear operator of interest, and we apply it to this thing that we use to define a phasor, with C being the phasor, then we're entitled to take the real part of the linear operator applied to this thing, and we'll get the same result. Well, let's go ahead and do this part. We'll take the time derivative of C, a constant, times e to the j omega t. We simply get j omega times what we started with. That's the result of taking the time derivative. And now if we look at this expression, it is in the form of a phasor. We have the real part of something, some constant, here it is, times the phase frequency operator, which has that frequency that we've assumed and suppressed. So what we have here is a phasor. And what we have found is that in the phasor domain, time differentiation is simply multiplication by a constant, simply multiplication by j omega. Let me say that another way. Differentiation by time in the time domain is the same as multiplication by j omega in the phasor domain. And that is incredibly useful because it's simpler. Multiplication by constant is simpler than taking a derivative. Let me give you a more specific example so you can see exactly what's going on here. Let me take C to be a real valued number. In other words, I'm saying C has magnitude A and phase of 0. So that corresponds to the sinusoid A times cosine omega t. Now let me take the real part of j omega A e to the j omega t. If I now expand this out using Eulers' formula, I get j omega A times the quantity cosine omega t plus j sine omega t. Now I multiply through the j omega A. I get a j omega times cosine minus a omega times sine omega t. Remember, j times j equals minus 1. That's where that minus sign comes from. So now if I take the real part, that's this thing here. This is the real part. This is imaginary valued because of the j. So the result is minus a omega sine omega t. Well, this is what we expected. This is the time derivative of a cosine omega t. The time derivative of a cosine omega t is minus a omega sine omega t. So this all checks. This confirms that I can, in fact, do these operations in any order. So, why should we care? Phasors make analysis much simpler. I've just shown you an example. I can apply time derivatives in the real waveform domain, or I can multiply by j omega in the phasor domain. This is almost invariably simpler than this. So there's a big simplification here by operating on phasors. And that's just one example. Another reason that we like phasors so much is because this theory is not restricted to sinusoids. The reason is because Fourier theory says that any physical waveform can be represented as a sum of sinusoids. For example, you know that a square wave can be represented by a sum of sinusoids. Any other physical waveform, not even just periodic waveforms, can be represented as sums of sinusoids. Also, we know addition, the summing that we do here, addition is a linear operation. So, phasor analysis can be applied to any physical waveform. In summary, this means that phasor analysis doesn't limit us to sinusoids. It really gives us a way to deal with any physical waveform. It just turns out that most of the time we're interested in sinusoids, but once we get an expression or we understand what's happening with the sinusoids, we can do very complex signals and take advantage of these simplifications that we get by being in the phasor domain. So here are some common pitfalls. These are some things that result in students making errors when they're doing phasor analysis. First, any waveform associated with a physical process is real valued. Let me say that again. If you're doing engineering and you're dealing with a physical process, it has real valued waveforms. We call the imaginary component imaginary for a reason. It's because it doesn't exist. We introduce imaginary quantities to make things simpler, to allow us to do things like phasor analysis. So don't ever say that a physical waveform has an imaginary component. Now, all the time we leave answers in phasor form. But again, that doesn't mean that that phasor is the physical thing. It is, again, simply a representation of the physical thing, usually a sinusoid. Phasors merely represent physical waveforms and are not the physical waveform. But you can always get back to the physical time domain waveform given the phasor. Always keep track of whether you are working in the physical domain or the phasor domain, and in what domain the desired answer should be. So a common pitfall is to give a phasor as the answer when a physical waveform is expected, or vice versa. And again, we frequently leave answers in phasor form, but you need to understand that that's the phasor and not the physical waveform. The most important point of all, a phasor is a complex valued number that represents a sinusoidally varying real valued waveform. If you keep this in mind, you are much less likely to make an error. This concludes this lecture on phasors.